We continue the introduction to differential equations, and next we will discuss one of the ways to visualize the solution of a first-order differential equation. And the topic is the direction for the slope fields. So first of all, let's recall what the derivative of a function represents. Let's assume that we have a function whose graph looks something like this, and the derivative of a function at some point A represents the slope of the tangent line to the graph of the function at that point. So if we take another point, we call this D, then this slope over here will be represented by f prime evaluated at the value D. And what do we know about the slopes? We know that slope determines the shape or the direction of the tangent line. So if we have a slope that is equal to 1, then the line will look like this. So we use the formula rise over run to figure out the shape. If the slope is 0, then the line is horizontal and it looks like this. If the slope is -1, then the line looks like this, and so on. So for any value of the slope, we should be able to figure out the shape of the tangent line. So the bigger the slope, the steeper the line is. So the smaller the slope, the flatter the line is, and the opposite is true for the negative values. So -3 means it's going to be steep in the other direction. So this is what we know. And when the derivative of a function is given to us by some expression rather than a number, what does that mean? So the derivative function, how we use the derivative function, we can use it to evaluate, to find the derivative at any individual point. So what does it mean? That means if we take some x value, then we'll be able to compute 2x, which is the derivative of the function, which happens to be the slope of the function at that point. And again, this is what we previously learned in calculus 1 class. So when x is equal to 0, 2x will be equal to 0, and therefore the slope of the tangent line will be equal to 0. When x is equal to 1, then the slope of the tangent line will be equal to 1. And vice versa, right? So this is what we know. Now, how does any of this apply to the topic of differential equations? So consider for a second the following equation. And as any differential equation, there is a derivative of a function, and this is a special differential equation in which we can isolate the derivative on one side and place everything else on the other side. And looking at it now, what do we see? We see that on the left-hand side we have y prime, which represents the slope of the tangent line at the point x, y. And on the right side, we actually have a formula that tells us how to find the slope of the tangent line at that point. So that means for any value x and y, we should be able to use the formula for x plus y plus 1 to compute the slope of the tangent line. Let's try and do a few computations. So when x equals 0 and y equals 0, what do we get? 2 times 0 plus 0 plus 1, it's 1. When x equals 1, y equals 0, we get 2 times 1 plus 0 plus 1, so we get 3. When x equals 1, y equals 1, we get 2 times 1 plus 1 plus 1, we get 4. And maybe we can go in the other direction, so maybe this is 0, this is 1, and then what do we get? 2 times 0 plus 1 plus 1, 2. And maybe we should try 1 with the negative 1, 0. So 2 times the negative 1 plus 0 plus 1. It's negative 1. And we should try negative 1, negative 1. 2 times the negative 1 plus 1. And that's negative 2. Let's try another point. So what do we have here? Let's do negative 1, 1. 2 times negative 1 plus 1 plus 1. That's 0. Let's do a couple more. So let's try reducing this with it. Negative 1. So we tried negative 1. Let's do 1, negative 1. So what do we have? 2 times 1 minus 1 plus 1. That's 2. And let's also try 0 and negative 1. So we have 2 times 0 minus 1 plus 1. That's 0. And again, it doesn't have to be whole numbers. We can do the same computations for fractions as well. So let's try 1/2 and 1/2. So we get 2 times 1/2 plus 1/2 plus 1. So it is 2.5. Now, what can we do with this? Well, we can recall the geometric meaning of the derivative or the slope, and we can imagine the slope of the tangent line at all of these points. So at 0, 0, the slope will look like this. At 1, 0, the slope will be 3, so it's going to be steep. At 1, 1, it's going to be steeper. At 0, 1, it's going to be less steep. At negative 1, 0, it's going to be negative 1. At negative 1, negative 1, it's going to be negative 2. At negative 1, 1, it's going to be 0. At 1, negative 1, it's going to be 2. At 0, negative 1, it's going to be 0. And at 1/2, 1/2, it's going to be somewhere between 2 and 3. So something like this. And what do we do with that? So with that, we can plot the those individual slopes at each of the individual points for which we computed them. So at 0, 0, the slope is 1. So at 0, 0, we can draw a tick mark that represents the slope 1. At 1, 0, we can draw a tick mark with slope 3, so it's going to be something like this. At 1, 1, we'll draw a tick mark that represents the slope 4, so it's going to be even steeper. At 0, 1, it's going to be the slope 2, so something like this. At negative 1, 0, slope is negative 1. At negative 1, negative 1, the slope is negative 2. At negative 1, 1, the slope is 0. At 1, negative 1, the slope is 2. At 0, negative 1, again, the slope is 0. And at 1 half, 1 half, the slope is 2.5, so it's something like this. So you can imagine doing this at every point, and eventually you will get what's called the slope field. Slope or direction field. So it goes by 2 names. So again, this diagram that we have created is what we refer to as the slope field. Obviously, doing it by hand, it's pretty tedious. So what we usually do is if we're really interested in slope field, we go to the Wolfram alpha and we simply type the differential equation, and one of the first things Wolfram alpha will do is will give you the slope field. Of course, it will also give you the solution, but we're not looking for a solution right now. We're looking for a slope field. Now, if we take the actual slope field and superimpose it into the diagram, so we have to be careful, right? Because we have 0, 0. The scale is a little off here. 0, -1. So we can see that our drawing of a slope field wasn't too bad, right? So more or less it looks about much better. So yeah. So this is what an actual slope field would look like if you do what we've done, but for many more points. Now that we know what a slope field is, let's try to figure out what is there we can do with a slope field. So let's consider this differential equation, and let's consider its slope field that looks like this. I got it from Wolfram alpha. So the first question is, what do we do? And here you have to understand that the slope field is the visual representation of the general solution. And if you remember, the general solution is the way to express all the solutions of the differential equation at once. So the general solution, if you want to visualize it, you're going to have a problem because you're going to have to visualize infinitely many curves. And whenever we see the word infinite, we know we're going to have a problem. So it's not going to be easy to visualize all the curves. However, you're going to have to somehow deal with the fact that they do exist, and this little tick marks show the slopes of the tangent lines to those curves at each of those points. So for some value c, we're going to have a curve that looks something like this. So I'm going to try to draw one carefully. Like this could be a the graph of one of the solutions of this differential equation, and it would be for some c1. And then if you pick a different value of c, you may end up with a different curve. So for example, like this could be c2, and so on. So we can have another solution here. This could be for some constant c3, and then we can have another solution here for some value c4, and again we have infinitely many of them. So this slope field allows us to visualize infinitely many solutions at once. So that's one thing that we can do with the slope field. On the other hand, if we consider the same equation and the same slope field, we may also, well, this time let's add some initial condition. When an initial condition is given, we should be able to visualize the particular solution associated with this initial condition. So unlike the general solution, the particular solution is one curve passing through what? Well, whatever your initial condition is. So in this case, if your initial condition is 0, 0, so x equals 0, y equals 0, then the particular solution will be the graph of the particular solution will be the curve passing through the point 0, 0. So if we identify the point 0, 0 in this field right here, and then the curve passing through this point is going to represent that particular solution that solves this initial value problem. So let's just sketch this curve. And to sketch this curve, we're just going to follow the slopes in the slope field. So at 0, 0, we have a horizontal slope, so the line is pretty horizontal. But the further away you get, you see how the slope field tells us that the line actually curves. So here it curves upward, and then it curves less, or say more, and more, and then it looks something like this. Going to the left, it's going to curve in the negative direction, so something like this. Of course, it's not accurate, but at least it gives us the idea of what the graph of the particular solution looks like. And sometimes that's all we need, because when solving differential equations, we may not necessarily be interested in finding the graph of the entire solution, but we may only be interested in answering a question like this. Find y of 1. So using this slope field, we can try and estimate y of 1 by simply finding the x equals to 1 on the x-axis, and then finding the corresponding y value. So in this case, without doing much work, I can estimate this value as 0.85. Again, this is just going to be an estimate, but notice how we provided this estimate with nothing but the slope field. So this is what slope fields are, and this is how we can use them.